Arrangements with some things alike. Well, let's see. For the last 26 years, actually, I've been in the Department of Statistics and Actuarial Science. I'm not complaining about my department, although I can because I don't think the chair's in the other room at the moment. The acronym for that department, whenever I get email, it's, SAS faculty. Which is okay. But actuarial science is a very, very important part of our department. And for 26 years, at most department meetings, if not all, that I've attended, I've raised that issue. It's clear that we should have far more prominence in our department for actuarial science. It's obvious that their name should come first. It should be the Department of Actuarial Science and Statistics. My argument for that is, first, it gives them the prominence they deserve, and second, it gives us an acronym that most of us are referred to anyway, so it's not going to change much. Anyway, how many ways can I rearrange a total of, in this case, 3 symbols, SAS, where 2 of them are alike? And in general, if I have n symbols, but there are n1 of one type, of a certain letter, and n2 of another, up to nk of the last, then this provides the number of permutations where we acknowledge that the A's can't be distinguished from each other and the S's can't be distinguished from each other, and so on. So that is a general formula which I'm pretty sure you've met before in any case. The number of ways we could have permuted the letters of SAS, so being very careful here, is 3 factorial divided by 2 factorial because there are 2 S's, and 1 factorial because there is 1 A. So, in fact, in this case, the number of permutations is 3. Or if you prefer, here's a simpler way of solving that problem, especially if there are more letters involved. Pick a place, pick a location for the letter A out of the 3 choices, and you're done. Once you've placed A, the S's have to fall in their place. Okay, here is an example. I think it's taken from the end of probably the end of chapter 3. 6 men and 3 women are sitting together in a row, actually are supposed to sit together in a row. Find the probability that the women all sit together. The first thing that goes through your head here is that this is probably a lousy model. You have 9 seats, men and women walk into a room and you say, sit down. I could do that here. I guess I could just check to see in a specific row how many clusters of women and men there are. In general, in my experience, they don't simply pick seats at random. The women sit together. Any place I've ever been, they sit as far as possible from someone who looks like me. And if Johnny Depp is there, they sit near or on him. So in fact, the model stinks. That may be the case for other problems you'll see. Bear with us. This isn't actually being used by men and women around the world to choose their seats. But if they did, what would the answer be? Well, there are a total of 9 seats, and the women, presumably, could pick any 3 of them. So 9 choose 3 is the number of ways that women could pick seats, or if you prefer, concentrate on the men. The answer in that case would be 9 choose 6. Whoops. And 9 choose 6 and 9 choose 3, fortunately, are identical. So whether you find seats for the men or the women, you get the same answer. Of course, once the women are seated, the men have to take their places, and the laws are such that they're not allowed to sit on a woman unless she asks them to. Now, how do we get the number of ways of them sitting so that the women are all seated together? Well, here is a trick, and you'll be able to use this, I think, again. I'm going to place them so that the three women I treat now as a single symbol, WWW. It's not world wrestling anything. That's just a symbol, WWW. So I'm going to place that symbol somewhere in 7 spaces, right? I have 6 spaces for men, 1, 2, 3, 4, 5, 6, and a 7th space for WWW. So I could place it here or here, any one of those 7 spots. In other words, this is easy. I'll just choose 7, choose 1 places for the symbol WWW, and that's it. The probability that women sit together, therefore, is equal to 7, or 7 choose 1, divided by 9 choose 3, which I think is equal to 84 or something. But I point out at the bottom of the slide that this solution is based on a very likely faulty assumption. Every now and then we'll ask you a question like this, and then we'll say, why does this solution or this question really suck? And you'll have to say something like, because women don't actually pick their seats at random. They're more likely to sit together or near someone they actually like. This is another problem which is just a combinatorial one, so let's knock it off in a few seconds. A factory produces 4 kinds of chocolate bars. This is inspired. I was on sabbatical in Switzerland, and I spent most of my sabbatical year visiting chocolate factories to collect problems just like this one. I also bought a lot of chocolate while there, and I charged it all to the department, so not to worry. A factory produces 4 kinds of chocolate bars, A, B, C, and D, on the same assembly line. The line runs 3 runs a day, and each bar type is produced at most for 1 run a day. Try and learn the lingo. At most means chocolate bar A could be produced once or no times in a day, but it can't be produced twice or 3 times.